So, let us look at a sample run of the A star algorithm. So, it starts from Arad and currently its G function is 0. I want everybody to answer these simple questions, so that you get used to the A star algorithm. So, G function is 0 because cost from the start state to me, which is start state, is 0, and my H function is the straight line distance between Arad and Bucharest, which is 366. So, initially this is the only node in the fringe, but then when I expand, I will expand to 3 possible nodes in the fringe. The 3 nodes would be Zerin, Sibiu and Timisoara. Everybody with me? This is the first child, second child and third child. Now, we need to figure out which node to expand further. So, let us look at them. For Zerin, my f function would be 75 plus 374. For Sibiu, my f function would be 140 plus 253, and for Timisoara, my f function would be 118 plus 329, and therefore, I am going to expand Sibiu because it is the shortest, it is 393. It basically says even though the current price that I am giving is high, the expected estimated distance further down is low, and so let us try to go there. Okay. So far so good. So, I expand Sibiu. When I expand Sibiu, of course, I also get Arad back because I can always go back to Arad, but notice now the f cost has become 140 plus 140 280 plus the original 366, which was the heuristic distance. So, it has become fairly high. So, hopefully, the algorithm will figure out there is no point going from Arad to Sibiu and then coming back to Arad and following up from there, and it will not get to the, it will not be picked in the fringe, and even if it gets picked, it will not be picked many times, right. So, now in my fringe I have 6 states, 6 nodes: Zerin, Timisoara, Oradea, Fagaras, Arad and Rumnicu Vulcha. Right. You can see I have done my homework. See, this will be very helpful to you when you go to Romania. You should plan your vacation in Romania now that you are so familiar with its map. And I am going to pick the node which looks the best for now, right. It could be Timisoara, or it could be which is the child of Arad, or it could be one of the children of Sibiu, right. And in this case it is another children of Sibiu. So, I expand Rumnicu Vulcha and I get to these 3 states, 3 cities. And notice that the best is now Pitesti, no, Fagaras, the best is Fagaras. So, at this point, what is my algorithm saying? It is saying maybe the best path is through Pitesti, but for now it seems like the best path might be through Fagaras. So, let me first expand it and double check that is there one or is there not one. So, I expand Fagaras, so I get to these 2. Now, as soon as I hit Bucharest, am I done? It is important. So, what I have found is, have I found a path to Bucharest? Very good. I have found a path to Bucharest, and the cost to the path to Bucharest is 450. However, there are nodes in the fringe whose f value is less than 450. What does that tell you? There may be another path through those nodes which may have lower total cost. So, let us not stop right here, let us keep going. So, then I expand Pitesti, and once I expand Pitesti, I get to another node of Bucharest. At the time I remove the goal from my fringe, that is the time I know that I have found the best path, and again we will prove some of these things, why best in what sense. So, when I remove Bucharest, that is when I found the paths that the algorithm returns, and algorithm returns Arad, Sibiu, Râmnicu, Vâlcea, Pitești and Bucharest as my final path, which is, if you go back to the map, Arad to Sibiu to Râmnicu, Vâlcea to Pitești to Bucharest. And the alternative path we have found is Arad to Sibiu to Făgăraș to Bucharest, but even though it has fewer number of cities, the distances are high, and so this is not the path that we return. Everybody with me on A star's functioning? Any questions? So, now comes the bigger question, and the bigger question is it going to be optimal? Okay. And here I am not going to ask you for intuitions, because there is a theory behind it, and it depends on how good the heuristic function is. It is possible that my heuristic function so confused you that you end up finding a path which is not the optimal. The optimal path was here, but the heuristic function was so bad that I never even expanded many of those states. It is possible. In fact, I urge you to construct such an example, it will be very easy to construct. Good. So, now the question is, when would this be optimal, and what do we know theoretically about it? And for that I need to define some notions of goodness of heuristic functions, and I am going to define two notions. The first notion is called admissibility. A heuristic function Hn is admissible, and I have written many words here, but first thing I want you to learn is that a heuristic function is admissible if it is optimistic. Okay. I want you to first learn this word. And what is optimistic? What is most optimistic? What is most optimistic? I am goal. What will be the heights of optimism for the node? The node will say, no need to search further, I am goal enough, I am God, right. So, the equivalent of that is I am goal. In other words, H will be equal to, come on, H will be equal to 0. If I am goal, then my distance to myself is 0. So, the most optimistic heuristic would be 0. But however, what will be the meaning of optimism? The meaning of optimism would be that the cost to the goal is estimated as less than what it actually is. You feel that I will have to pay less cost than you actually end up paying. That is the meaning of admissibility. If however, you are in a place where you want to make money and higher is better, what is an admissible heuristic? One which makes you believe that you will earn more, not less. So, any day if somebody asks you, is heuristic function means it is always less than the optimal, say no. Admissible heuristic is not always that is less than optimal, it is less than optimal for or less than equal to optimal for minimization problems, but it is greater than equal to optimal for maximization problems. Everybody with me so far? So, but because we are in the minimization setting, a heuristic function Hn is admissible if for every node n, Hn is less than equal to the optimal true cost to reach a goal state from n. That is, an admissible heuristic never overestimates the cost to reach a goal, i.e., it is optimistic. And now you can ask the question, is this straight line distance admissible? Because the shortest flight you can have is the crow's flight. After that, you will end up diverging from the straight line and you will end up paying more. So, therefore, the straight line distance is actually an admissible heuristic. And moreover, and there is a theorem, and you have to do all proofs, but we will discuss one of them only. If Hn is admissible, then the tree search version of A star is optimal. Okay. We will prove it soon. But the interesting thing is that if it is the graph search version, then admissibility is not sufficient. It is a necessary condition, but not a sufficient condition. And so, we need to define a new condition to figure out when would the graph search version of A star be optimal, and that condition is called consistency. Okay. And Hn is consistent if for every node n and for every successor n prime due to some action A, the triangular inequality is satisfied, which basically means that the estimated cost from n to the goal is going to be less than equal to the actual cost that you pay right now when going from n to n prime, and the estimated cost of the from n prime to goal. Okay. And in fact, you can prove, and I would let you do this as homework, you can prove by induction or whatever, that every consistent heuristic is also admissible. And now you can also prove that if a heuristic is consistent, then A star using graph search is optimal. Okay. So, there are 3 things to learn here, okay, and understand. 1, when is tree search version of A star optimal? When the heuristic is admissible. When is graph search version of A star optimal? When heuristic is consistent. But believe it or not, consistency subsumes admissibility. So, if you are consistent, you are anyway admissible. And moreover, we need to get some intuitions as to why this is the case. Okay. So, we will do some intuitions, there are more, but we will not study all of them. So, first I want to do one simple example of what happens if we have admissible heuristic, but we are doing graph search version of A star. This example will help clear your concepts on graph search version of A star. So, let us do that, and we will do this with this example. So, let us say my objective is to go from start state to goal, and I can go to A or B, I can go from B to A, and then I can go from A to goal. It is a relatively simple example, and the H costs are mentioned 2, 4, 1 and 4, and the heuristics are mentioned on the nodes H equal to 7 for state S, H equal to 5 for state B, H equal to 1 for state A, and of course 0 for goal. So, the first thing we need to check is whether H is admissible. What is the shortest path, by the way? What is the shortest path we are looking for? What is the shortest path we are looking for? SBAG. So, SBAG is the shortest path we are looking for, and what is the cost for that? 7. And now, is this heuristic admissible? So, what is the shortest path from A to G? What is the cost? 4. And what is the heuristic? 1 is less than 4? Good. What is the shortest path from B? Cost? 5. What is the heuristic? 5 less than or equal to the optimal, heuristic is admissible. The best cost from state S is 7, and what is the heuristic? 7. So, therefore, we can prove that H is, or we can verify that H is admissible. Now, what we are going to do is we are going to run the A star algorithm on this particular example, just to show that it messes up tree search version of A star. Okay. So, let us do that. So, we will start from the start state, and when we expand it, we can go to A or we can go to B, and when we go to A, what is the F value? 5, 4 plus 1, and what is the B, F value for B? 7. What is in my fringe right now? A and B, and which one am I going to expand? A. Now, notice that this is the graph search version. So, when I expanded S, what did I put in my explored list? I already put S in my explored list, right, and my open list or my fringe currently is A and B. Now, when I remove A, then I remove it from the fringe and I add it to the explored list. And what are the states where can I go to from A? I can go to G. What will be the f value of G? Okay, this is careful, be careful. What will be the f value of G? 8. 4 plus 4 plus 0. So, my f value of G would be 8. So, I will add G into the fringe. Now, what is in my fringe? B and G is in my fringe, right. I do not stop until I remove goal. So, B and G is in my fringe. Now, comes the key step. When I expand B, I will get to A, and when I go to A, it is already in explode list. Because it is already in explode list, am I going to add it in the fringe? No. So, basically I just remove B and expansion leads to nothing, and I added B to explode list. So, what just happened? I lost my optimal path, which was SBAG in this process. And why did I lose it? Because earlier I have already expanded A. And why did I expand A? Well, I expanded A because A was looking too close to goal. But now that I have expanded it, there is no way to resurrect a newfound path to the node that was already expanded, newfound path to A. So, in order for this to work, I need to somehow prove that no new shorter path to this node can be found when I am removing it from fringe and adding it to explode. And this can happen if your heuristic is consistent, but this does not always happen if your heuristic is admissible. Okay? So, there is a proof in the book which shows that the graph search version of A star is optimal if you expand using consistent heuristics, but the goal the proof says that I will in one path f's are always in a non-decreasing order, and that is sort of the fundamental basis of that, which I would encourage you to read. But this example shows you that the algorithm can be fooled when I put something in an explode list and then later a better path is found, which can happen if your heuristic is only admissible but not consistent. Yes, question. Say that again. Yes. Why is SAG 8? Why is it 8? Because S to A is 4 and A to G is 4. So, that is why it is 8. See, this is 4 and this is 4. No, this is not heuristic, this is the G function. H of the goal is going to be 0. Does that make sense? This is important. Why would f value for goal be 8? Because f value is always G plus H. G is the actual cost to the goal to the node, and H is the estimated cost in the future. Estimated cost in the future is going to be 0. The actual cost is going to be 8 because I am following this H and this H. Okay. Good. So, that was one example. This example is from Stack Overflow. It is a nice example. I like it. We can stop here. Thank you.